Newton did enough work with his formula for derivative. And remember, Leibniz was working in Germany, Newton is working in Great Britain and England, and working with this limit. And he started to notice patterns. He started to notice enough patterns that he was able to come up with some shortcuts. So today I'm going to show you some of the shortcuts, not all of them, but some of them that will help your processes go a little bit faster. We're going to use the first shortcut, which is called the power rule, which you'll love. Okay. Then we're going to learn what to do when you have a negative power. And we're going to learn that there's such a thing as first derivatives, second derivatives, third derivatives, and more. We'll finish all of that by 10 o'clock today. All right, so here we go. I need you to train your brain to when I say the word derivative, you automatically think slope. Okay, just associate those two things together. They are interchangeable. Sometimes when you're reading a problem, it might even be helpful to you to especially if it's an FRQ and you're writing on it, to cross out the word derivative and put the word slope in to help train your brain for that, okay? So that's going to help you with this first rule, this first property. This is a shortcut rule for a derivative. All right, if the function is defined as a constant, okay? Now think graphically. What does the graph of a constant look like? Be more specific. What kind of a line? A line like this? Is that the graph of a constant? A horizontal line. Please be specific, right? Okay, because there's lots of different kinds of lines. The graph of a constant is a horizontal line. So what does that mean about the derivative of every constant? And if we change the word derivative to slope, that should help you answer the question. All right, if you're asked for the derivative of a constant, if the graph of a constant is a horizontal line and the derivative means slope, then what is the slope of a constant? 0. There's your first shortcut. The slope of every constant is 0, so the derivative of every constant is 0. You don't need a limit to prove that. The derivative of every constant is 0. All right, the next one. What if you have a constant and a variable? Okay, what if you have C and U together? Again, think of it as a graph, and then think of the word derivative being the word slope. Okay, C times a variable. For example, 4x. That's a constant times a variable. Or half x. Or negative 5/7 x. Okay, what shapes are all of those? Okay, and what makes them different from being a horizontal line? They have different slopes. We call those oblique lines. Okay, so all of these are, what they have in common is that they are all oblique lines. What is the derivative of every oblique line? Or replace the word the derivative with what is the slope of every oblique line? Whatever the constant is out in front of it, right? If I say 2x, then the derivative is 2 because the slope is 2. Okay, if I say negative 4x, the derivative is negative 4 because the slope is negative 4. If I say 5/7 x, the derivative is 5/7 because the slope is 5/7. And so the derivative of all of these is whatever C is the constant. So now you have two shortcut rules that you don't need to use limits for anymore. But both of those things deal with straight lines. So what if something is curved? What?
I said the power rule.
What if something is curved? All right, here we go. If you have something that has a power, an n, that curves your graph. It could be a square or a cube or a fraction. It could be a half. It could be anything. If you have a number there, that's going to curve your graph. So how do you find the derivative for that? So Newton did this over and over and over and over again, and he figured out a pattern for this consistently. He found out that a cube always has a derivative that's a square. And a 7th function always had a derivative that was a 6th function. And he started to wonder, it's always one less. And so then he tested it, and over and over he was able to prove that that is true, that the derivative is always 1 less. So here you go. If you have a cube, then a power function, your derivative will be 1 less. Take 1 away, and then you have the derivative. However, it's not just that simple. You also have to multiply it by what the n was in the first place, the power in the first place. So you multiply by the coefficient of the power, and you always lower the power down by a value of 1. This is the shortcut to doing the limits. So let's practice that. If you have the curved function 5x to the 4th, can you use this rule to find its derivative? So according to the power rule, what will the power on the derivative be if it's 1 less than the one it was before? 3. But what will the coefficient be out in the front? It'll be 20. Okay, why is it 20? Because there was a 5 there, and then I have to multiply by the 4. This is what you get when you do the limit rule. So if I ask you to prove it, you might have to prove it to me. But the shortcut is that this is what it works out to be. It works for fractions. It works for fractions or square roots because they are fractions. So then what would the derivative or the slope be? So then you say, well, okay, the x has to have a power that is 1 less than what it used to be. So what is 1 less? Negative 1/2. But what do I do with the original positive 1/2? It goes out in front. And that's something you would never leave as a final answer because it has a negative in it. And so you need to put this into its fraction form. Okay? Hi, thanks. So the fraction would say that 1 is in the numerator, 2 is in the denominator, and so is the square root of x. Please don't ever leave a negative. Please make sure that you are simplifying it. You don't have to rationalize, but you do have to simplify. All right, h of x. Power rule works for this too, as long as you rewrite it as x to the negative 3. So you were temporarily using a negative so that we can find the derivative. What will the power on the derivative be? Negative 4, because I just subtracted 1. And then the original negative 3 goes in the front. And so that becomes a fraction. The numerator is negative 3. The denominator is x to the 4th. Okay, are there any questions so far about the power rule? Saves you a lot of time. Okay. Rule number 4. If the original problem has addition and subtraction in it, then the derivative will also have addition and subtraction in it. So it would say that we take the derivative of u first, and then we add it to the derivative of v. Okay, this is Leibniz's way of writing it. He used the fraction d dx to talk about derivative, but that you are allowed to do separate derivatives. Addition and subtraction is fine. Multiplication is not fine. Multiplication needs a whole different rule, but addition and subtraction is fine. So that helps us with a problem like this. This is a problem with subtraction in it. All right, the overall directions are for us to find a tangent line, which is the same as what we were doing yesterday. So we find a point first, and then we find our slope. The point at the number 1, when I plug the number 1, will be 1, 3. The slope will be whatever the derivative is. So my derivative has 2 power pieces, and I just lower the powers on both of them. So I know that my derivative is going to start with a squared because it used to be a cube. But what number goes in front of that? 18. Good job, Tyler. Okay, why is it 18? Can you explain it? Okay, there's a 6 that was already there, and you also multiply it by the 3. All right, then we subtract. The next one is just going to be x because we're lowering it from a squared down. And then the coefficient in front of that is 6. Now that is called the derivative. It's not the slope yet. The slope yet, we have to plug the number 1 into that to actually figure out the slope. So this is not yet the slope. So I should maybe correct this. This is the derivative. And my slope is going to be f prime with the number 1 plugged in. So then I plug the number 1 in, and I get 12. So then I can write my tangent line. And my tangent line will be y minus 3 equals 12 times x minus 1. That's my tangent line. It's a lot faster than needing to use the limit every single time once you know the power rule. Okay, how about finding the tangent line for this one? All right, our curve is that. So we're going to have a point, we're going to have a derivative, and then we'll use the derivative to find our slope. Our point is 1, 1. Our derivative is going to be y prime. The way the original function is given is not in the best format for derivatives, so you need to think of that differently. You need to think of your hyperbola as x to the negative first so that you can find its derivative. All right, so I need a volunteer to find my derivative. Okay, Andre.
So you change it to x to the negative first?
I did. I changed it to x to the negative first. Okay, and so what's the derivative going to be? X to the negative what?
Negative second.
X to the negative second. But what do I do with that original negative 1 that was there? Okay, so put it in the front. All right, so that is my derivative. And then what will that look like in its simplified form?
Negative 1 over x squared.
Okay, so that is the derivative. And now we will use that to find the slope by plugging the number 1 in. So that would be negative 1 over quantity 1 squared, so negative 1. So my tangent line is y minus 1 equals the slope of negative 1 times x minus 1. Then the next question following up on that is, well, what's the normal line? And remember, normal having the meaning of perpendicular. Okay, Luke, you want to try that one?
1/2.
So you're only going to change this.
Yeah.
All right, so just tell me the whole normal line.
Y minus 1 equals, is it 1/2?
Where are you getting a 2 from? It is just 1. The reciprocal of 1 is 1. And then x minus 1. Okay? You do not ever need to distribute. Leave your tangent line in point slope form. People make more mistakes distributing and then trying to put it in y equals mx plus b when it's not necessary. Leave it like this, and it's easy to switch from normal to tangent and back and forth. Just leave it in its point slope form. All right. Now, here's, we're kind of pushing things a little bit. This is a little bit more of a challenge. Does the curve x to the 4th minus 8x squared minus 2, which is, or plus 2, which is graphed there, we call that a quartic, does it have any places of a horizontal tangent? A horizontal tangent means the tangent line has a slope of 0. I can look at this, and I can count the number of places where there would be a horizontal tangent. My first horizontal tangent I see right here. Okay, I see 2 more down here and here. Okay, but seeing is not proving. What do those 3 horizontal tangents have in common with each other? What do they all have that's the same? Yeah, the slope is 0 at all of them. And replace the word slope with what we're learning now. Okay, the slope or the derivative is 0. If you can understand that, then you can solve this question, because you just need to find where the slope or the derivative, or aka the derivative, is 0. That is our job. So find where y prime equals 0. Not just looking, seeing is not proving, but doing the math is proving. So we want to find y prime. All right, is anybody feeling good about finding y prime? Maybe Ian wants to try? Find our y prime for us? Okay, what is it going to start with? X to the what? 4 cubed. Okay, and then I can subtract, and what's the next one going to be? Okay, and then what about the derivative of 2? Is 0. All right, and now I want to set that equal to 0. And now my calculus is done, and I'm back to algebra again. I solve this, keeping it set equal to 0 by factoring out a 4x, which leaves me with x squared minus 4. I factor that. That leaves me with x minus 2, x plus 2. And so I have a solution for each of those factors. I have a solution for the 4x, which would be 0. I have a solution of 2, and I have a solution of negative 2. These are the 3 places where I have horizontal tangents on my graph. To write those horizontal tangents, I need to make them all into points, and then I would have their slope to be 0. So in order to finish that, I would need to know what the y values are to make them all points. So my points are going to be 0, 2, and 2, let's see, 16 minus 14. And then my other one is negative 2, negative 14. Those are my 3 points. And then I would write 3 tangent lines to go with those 3 points, all of which would have a slope of 0. All right, to finish this up, we're going to talk about how derivatives can be repeated over and over again. All right, the first derivative of y. We've already shown how Newton and Leibniz both wrote that. Okay, Newton wrote f prime. Okay, that was his symbol for the first derivative. Leibniz wrote dy dx. Okay, that is the first derivative of y with respect to x. That means it's using x as the variable. That's what with respect to x means. It means it's like an equation that has x in it. If it said with respect to a, then the equation would have a in it. If it with respect to w, the equation would have w in it. The second derivative, okay, Newton would write it like this, with a double prime. And then Leibniz would write it like this. He snuck a little 2 in there to be the second derivative. And then the third derivative would be 3 of those, triple prime, and then sneak a little 3 in there. Okay, those are just the notations. So that just means, okay, take the derivative once, take the derivative of that, do it again, take the derivative of that, like just keep taking the derivative over and over and over again. All right, so let's try that with this one. Find all the derivatives possible for the polynomial that starts out as x to the 4th plus 2x squared minus 3/4 x minus 19. So we're going to find the first derivative, and we're just going to keep going and find as many as we can until we run out. Okay, David, can you do the first one? The first derivative of that? 4x to the power of 3 plus, okay, 4x.
And minus 3 over 4.
Okay, minus 3 over 4 minus
0.
minus 0. Good. Okay, that's the first derivative. Okay, second derivative. Okay, Brandon, you want to do it?
12x to the second.
Good.
Plus 4
Minus
minus 0.
0. And nothing else after that. All right. D3. Leela?
24x.
24x plus 0. Okay. D4. Noah? 0. Okay. And then,
It's 24x. 24x.
oh, we're missing an x. All right, so this one's not 0. What is it? I think I forgot to write it. That one's 24. Okay. Oop. D5. Now we're to 0. And from there on, everything else would be 0 the rest of the way. Okay. So we were able to get 5 derivatives out of that. Yeah.
Are you able to use Newton's and was it Leibniz?
Mhm.
Notation interchangeably?
In one question, like they'll usually, whatever notation they give you, like if they say find f prime, then the rest of that problem use prime. If they start with say find dy dx, then for the rest of the problem use, you'll get comfortable with both of them, back and forth, back and forth. Newton, by the way, once you run out a f triple prime like that, the next one is, you got to know your,
Oh, that makes sense. I was like, you don't write that.
no, yeah, you don't want to keep going. Okay. All right, perfect. Any other questions? Okay, then can you quickly, since we've got 3 minutes left, can you pull up